do it a little bit differently this time. So I'm going to solve a problem from OpenStax College Physics, Chapter 8. And this is problem number 36, and I didn't write anything down. Okay, so I'm going to read the question and then process it that way so you can see I can set up good problem solving strategies. That's my intention. Okay, so the problem says, I'm looking at my computer right here, a 30,000 kilogram freight car is coasting at 0.85 meters per second. Stop. I'm not going to read the rest. I'm just going to draw that, right? So I have a freight car. It's got wheels. It probably has more than two, but that's fine. I'm going to put a ground. You don't have to put a ground. I'm going to put the mass of 30,000 kilograms, and then I'm going to call this V1 because I think it might change, and that was 0.85 meters per second. Let's just double check. It says 30,000 kilograms, 0.85 meters per second. Okay, and it says negligible friction, so I don't have to worry about any frictional forces. And it's under a hopper that dumps 110,000 kilograms of scrap metal into it. So I'm going to race the 36, and I think this is like a hopper with stuff. It's going to fall in there. And the mass, so this is mass of the car, mass of the stuff is 110,000 kilograms. Okay. You see, I don't even know what they're asking. I just drew a picture, I wrote down everything that I was given. And that's one way to process this information. Next, A, what is the final velocity of the loaded freight car? So I'm going to put that down here, A, V2 equals. And then B, how much kinetic energy is lost? So I'm going to put B, delta K equals. Okay, so why would this be change? You know, you could think of this from a momentum perspective, and let's do that. So the first thing I want to do is to define my system. And my system is going to be MC plus MS. It's the stuff plus the car. And in that case, are there any external forces on the system? And you could kind of say yes. You could kind of. It's a kind of a weird question. You could kind of say that because there's a gravitational force pulling down the car on the coal. So that's an external force. There's a gravitational force pulling on the cart, and there's an upwards pushing force from the ground. But that's not going to be constant, right? As that stuff falls in there, the normal force is going to push up more. And yes, the center of mass of the whole system is going to move down because the stuff was up here and it's down there. But overall, we can just ignore the vertical direction and just focus on the horizontal direction. So in that case, there's no friction, there's no external forces on here. So if the system consists of those two, I can say the initial total momentum in the x direction is the final total momentum in the x direction. So I'm using 1 for initial and 2 for final, and that's just the x direction. And I'll talk about that in a second. Well, let's just write down what we know, right? I know the initial velocity of the car. I know the initial x velocity of the stuff. So let's write that as mass of the stuff times 0. It's not moving in the x direction before it falls. Plus mass of the car times, I'm going to just write this as V1. That one had no V. And then after they're stuck together, I should put this over here. I already did that. So here's after I have the car moving with the velocity V2, and it's got stuff in there. So it's kind of like an inelastic collision. I can say the mass of the stuff plus the mass of the car is V2. It's the final velocity. So here I have the initial momentum, here I have the final momentum, and I can say that because there's no external forces in the horizontal direction, and that was key. So if friction was there, I couldn't say that, right? Because it'd slow down all by itself. Okay, so I want to solve for V2. That's not too hard. V2 is going to be this times 0, which is 0, MC V1 over MS plus MC. Let's put in our values. The mass, I'm going to do something a little tricky because I'm lazy. I'm going to put the mass of the car is 30. It's 30. And it's not going to matter. I'm going to divide by 1,000. So I was going to say kilograms. which it would be kilograms. So it's 30 kilograms divided, and this times V1, 0.85. And then this is going to be 110 kilograms plus 30 kilograms. And you may think, why would you do that? Because I don't want to have to enter all the zeros, and they're all going to cancel, right? So the mass cancels because these two have the same mass units in kilograms, and that has the same units, so it cancels. Now, we can't do that for the energy, but that's fine. We're going to do it now anyway. So let's put this in our calculator. Drop 30, enter, 0.85 times, that is divided by 30, enter, 0.85 times, and then this is going to be 110 plus 30 is 140, so 140 divided by, and I get 0.182 meters per second, because that's in meters per second. Kilograms cancels, and that's our speed. So it did slow down. That's a good thing. It slowed down quite a bit, but we also added a lot of mass, a lot. Okay, now let's find our change in kinetic energy. We can just do as the initial kinetic energy minus the final kinetic energy. So K1, delta K is going to be K2 minus K1. So it's going to be the final kinetic energy, 1/2 mass of the car plus mass of the stuff times V2 squared minus 1/2 mass of the car times V1 squared. Right? Because before the other thing wasn't moving. Oh, I should put that over here. That's what I've been doing. I've been 0.182 meters per second. That's that answer. Okay, I'm going to erase that stuff because I'm running out of room here. Okay, I'm gonna just calculate this. It's not too hard. So delta K. Now I do have to put in the actual mass because if I want the units for energy in joules, this has to be in kilograms. So I have 1/2. The mass of the two things together is 140,000 times the initial velocity, the final velocity, 0.182 squared minus 1/2. 30,000 running out of room times 0.85 squared. Okay, let's put that in. Drop. Oh, I shouldn't drop. 0.5, enter. 140,000 times 0.182 squared times. Now I'm going to do that other one. 0.5, enter. Did I do a half? I think I did. Okay, I'm going to drop. I'm going to start over. I'm not sure that it did. So 0.5, enter, 140,123 times 0.182 squared times, now I'm going to do that one, 0.5, enter, 30,000, 123 times 0.85 squared times minus. And I get negative 8518 joules. So that's the amount of decrease in kinetic energy. Now, let's talk about energy and then we'll talk about momentum because there is something important here. So, if the car decreased in energy, what happened? Well, if I have the system of the cart plus the stuff, then work is the change in energy. Now, what forces do work on the system? Well, nothing. I mean, you could say gravity does because it falls, but we're not, let's just say that it falls like that high. Then what does work on the system? Nothing. So I have 0 and I have delta K. So 0 is negative 8,518, which seems like it's kind of low, but I'm just going to go with it. Well, obviously there has to be something else here. There has to be some other type of change in energy. Since the kinetic energy decreased, that has to increase. What would that be? Thermal energy, sound, deformation energy, elastic energy of the compression of stuff. So there's other ways to quantify that energy. We didn't lose energy. Okay, that's the number one thing. Now, let's go back to the momentum. The momentum's constant, but why did the car decrease in speed if there's no backwards pushing forces on it? Let's say we want to think about this in terms of Newton's second law. Why does the car slow down? Well, there has to be something pushing backwards on it, and there is. Imagine as this car is moving this way, and you're putting stuff into it, it's going to fill up not evenly. It's going to fill up like that, right? Because that stuff's going to get pushed up against the wall. That back wall is going to have to push on that, on the stuff. And you could actually treat this as two different problems. The stuff speeds up and the car slows down. The stuff speeds up because the car pushes on it, and the car slows down because the stuff pushes on it. So that's one way to think about it. Okay, it wasn't a complicated problem, but maybe it was useful. The end.